Okay, the next topic here is about electric potential due to a single point charge. Okay, so for that we consider this is a single point charge plus Q, which is lying at a point O. Now I want to determine the electric potential at a point P, which is at a distance R from the source charge. Okay, so for that I will consider first a test charge, okay, which is lying at infinity, and this test charge is plus Q naught. Now I will move the test charge from infinity, let's say, to a point A, which is at a distance x from the source charge. Now as you move the test charge from infinity to a point A, that means towards the source charge, then the test charge will experience a force of repulsion by the source charge. And from Coulomb's law, we have seen that the force of repulsion between two charges is F is equals to 1 upon 4 pi epsilon naught Q1 Q2, but your Q1 here is this is Q, your Q2 is Q naught, upon square of the distance between them is this much. So this is the force of repulsion which is experienced by the test charge, and this force, it is directed from left to right, I mean along this direction. Okay, now if this test charge which you have placed at a point A, now let's say it is further moved to a point B through a distance dx against the force of repulsion. So in doing so, if you further move the test charge through a small distance dx, then small work has to be done, and that small work, right, to move the test charge over the distance dx is dw is equals to f dot dx, because we know the, right, I think this is clear to you because work done is equals to the scalar product of force and displacement. Now as you know, a dot b is equals to ab cos theta, so f dot dx will be f dx cos theta. But in this case your theta is 180 degree. Why it is 180 degree? Because look at the figure, f is acting in this direction and dx you are shifting this side, so the angle between dx and f, right, is 180 degree as they are anti-parallel to each other. Okay, so that is why we have cos 180. So cos 180 is nothing but is equals to minus 1, so minus 1 times f dx will be minus f dx. So this is the small work done to carry the test charge through a small distance dx. So if this is the small work done to carry a test charge through a small distance, then the total work done to move the test charge right from the position infinity to a point P whose distance from the source is r can be obtained by integrating this equation with the limits of integration from infinity to r, right, f dx with this. So instead of f we write that value. Okay, now this 1 by 4 pi epsilon naught is constant, so we take it outside. Q naught is constant, take it outside. So the only variable here is x, so we integrate, right, 1 upon x squared dx, or we can say dx upon x squared. Now for this you have to use this formula, integrations of x to the power n dx is equals to x to the power n plus 1 by n plus 1. So but here this x to the power 2, which is in the denominator, when you take it up it becomes x to the power minus 2. So in that case this x to the power n dx becomes x to the power minus 2 dx. So right, just applying this formula here, your n is minus 2, so you'll get x to the power minus 2 plus 1 by minus 2 plus 1. Minus 2 plus 1 is minus 1 like this, so you will get x to the power minus 1 upon minus 1. So now this minus 1 I'll take it out, and if you multiply with this minus it becomes plus, so you'll have only q naught upon 4 pi epsilon naught 1 upon x, and the limits of integration is from infinity to small r. Now substituting the limits of integration, the upper limit here is small r, so instead of x we write r, minus, again you substitute the lower limit which is infinity, instead of x you write infinity. So this is 1 by r, but we know 1 by infinity is equals to 0, So this terms will gone and you'll have only 1 upon r. So therefore the work done, okay, to carry the charge from infinity to a point P whose distance from the source charge is r is equals to this much. So this is the work done. So if this is the work done, then what is the electric potential at a point P? From the equation, from the definition, the electric potential is equals to work done by the charge you are moving. So the work done is equals to this, and the charge moving is q naught. So substituting the value of W, then you'll get like this, and you cancel q naught. So finally the electric potential at a point P, it is equals to this much. So please note down this formula, which is the required expressions for the electric potential due to a single point charge. Alright, and a point to be noted here is that the electric potential at infinity is equals to 0.